Hello, everybody. Welcome to our webinar on the LunaRecycle Challenge focused on NASA's approach to sustainability and managing waste on the moon with a tie to terrestrial applications. We're just going to wait about a moment or two to let everybody in from the waiting room. And then we will get started right away. You'll see a poll pop up as you enter. Please feel free to answer that so we can learn a little bit about you. Okay, it looks like everybody has joined us from the waiting room. So thank you all for joining us today, and welcome to our third webinar for our LunaRecycle Challenge. My name is Chris Frangione, and I am the Acting Challenge Manager for the LunaRecycle Challenge. Today's webinar is focused on NASA's approach to sustainability and managing waste on the moon with a tie to terrestrial applications. So this is not a detailed webinar on the rules of the challenge. You could always find that at our website, lunarecyclechallenge.ua.edu, which is in the lower right-hand corner of your screen. That has all of our rules, our documents, our templates, etc. Today's webinar is meant to serve as a foundation for you to understand what's currently happening. So if you choose to participate in our challenge, which we hope you do, you'll have a little bit of background information. First, some quick housekeeping. Today's webinar will be recorded. We will post a recording on that LunaRecycle website in the lower right-hand corner, and we will share it. We will also share that website again at the end of the webinar. Although you will not be able to turn on your video or microphones, you will be able to ask questions of our presenters using the Q&A function at the bottom of your screen. Please also don't raise your hand. We cannot answer any questions via raised hands. Everything needs to be put in that Q&A function. By using that Q&A function, we will have a record of all the questions that were asked. And although we may not be able to answer all of them today during this webinar, all questions that are relevant to the challenge, meaning about rules and eligibility and that kind of stuff, will be answered on our website in writing a couple weeks after the webinar. Please only submit questions in English. We will not be able to answer questions that are not submitted in English. We appreciate you submitting them in English. You'll also see a couple of polls pop up during the webinar. We ask that you answer these because they really provide us with important information on what you are interested in learning more about and how we could best support you as a potential solver. Finally, we have 3 great presenters and also a few others joining us to answer questions. Please note that what these presenters share are their opinions and do not necessarily represent the LunaRecycle Challenge as a whole. For any rules or eligibility related information, the only official information is that is found on our LunaRecycle website, again, in the lower right-hand corner. Okay, so we'll quickly go over the agenda and then we'll get to the meat of it. So we'll do a quick refresher on the LunaRecycle Challenge, what it is, how does it work, and some key dates. Then we will focus on NASA's approach to sustainability and waste management on the moon, and then a little bit on what some folks are doing on Earth, so you could see how they are related. Then we'll get into, we'll answer questions following the presentations. So you will be submitting questions during the presentation, so feel free to do that, but all questions will be answered following the presentations. And then I'm going to quickly share the bios now so that we could get to the speakers. So Ray Pitts is a waste management researcher at NASA Kennedy Space Center. His work largely focuses on methods to reduce, reuse, and recycle waste materials that are generated during exploration space missions. In this area, Ray has led technology development projects, waste modeling and characterization analyses, and architectural level trade studies to better understand when, where, and what waste processing techniques may be advantageous for future missions. Ray has been with NASA for 5 years, holding a BS in aerospace engineering from the University of Arizona and an MS in aerospace engineering from the University of Colorado at Boulder. Then Mike Ewert will be joining us. He has been a thermal and life support system engineer in the Crew and Thermal Systems Division at NASA Johnson Space Center in Houston, Texas for the past 35 years. He has performed analysis and testing in various technology projects involving thermal control, life support, and habitation systems. He is currently the systems engineering and integration lead for NASA's Logistics Reductions Project and chief technologist in the Crew and Thermal Systems divisions. He earned a master's degree in mechanical engineering from the University of Texas at Austin and holds several US patents. And then we have somebody speaking on terrestrial applications. So Ramona Carey is the Managing Director of Engineering and Administration at the Solid Waste Authority of Palm Beach County, SWA. He manages the authority's engineering, environmental programs, finance, purchasing, equal business opportunity, IT, education, and public affairs departments. He has more than 30 years of industry experience. He is a licensed professional engineer in the state of Florida and is a board-certified environmental engineer with a specialty in solid waste. He holds a bachelor's and master's degree in civil engineering and an MBA in international business. Mr. Carey is an active member of the American Society of Civil Engineers, Solid Waste Association of North America, Florida Engineering Society, and served on the board of the American Public Works Association Gold Coast, Florida chapter. He also serves on the advisory board of the Hinckley Center for Solid and Hazardous Waste Management. In 2012, Mr. Carey was named the ASCE Engineer of the Year, Palm Beach chapter. Prior to joining the authority, Mr. Carey was a consultant for 20 years with 3 different leading civil and environmental engineering firms, managing various solid waste management and civil environmental engineering projects for public and private clients. So those will be our speakers. When we get to the questions, we're going to have Annie Meyer join us. She's a technical lead for In Situ Resource Utilization, or ISRU, and Logistical Waste Management Systems in the Exploration Systems and Development Office at NASA Kennedy Space Center. Her focus is on applied research for space mission logistical waste conversion, resource extraction, and resource reutilization for human spaceflight in transit and on other planetary surfaces. Annie has led drop tower zero gravity facility and suborbital rocket test flight campaigns for waste conversion technology and advancement. Additional areas of focus have included in situ resource utilization applications, including Mars carbon dioxide conversion and lunar regolith oxygen production. As I mentioned, Annie will not be presenting, but is one of our top experts in this field. And she helped us design this challenge. So she's going to be a great addition to our panelists to answer questions. And our panel will be moderated by Jennifer Edmondson. Jennifer earned her PhD in Earth and Planetary Sciences at the University of New Mexico while studying the geology of the Moon and Mars. She came to Marshall Space Flight Center as a postdoc in 2008 and joined the Planetary Regolith Simulant team as a contractor in 2009. She participated in the Manufacturing Innovation Project starting in 2010, which ultimately became In Space Manufacturing, or ISM. Following the ISM motto of "Make it, don't take it," Jennifer began using her knowledge of lunar and Martian geology to participate in and grow planetary in situ resource utilization-based efforts at Marshall Space Flight Center, including the Moon to Mars Planetary Autonomous Construction Technology Surface Construction Project. She became a civil servant in 2020 and is currently the Impact Project Manager and Acting Centennial Challenges Project Manager. Centennial Challenges is the organization that puts on this LunaRecycle Challenge. Her primary interest is in enabling technology development for exploration and a sustainable human presence off Earth. So as you can see, we have great speakers. And so I'm going to just do a quick background on the challenge itself, and then we will get into their presentations. So as a reminder, we're not going to go into detail on these rules. You can find them on the website, which we will post again at the end. So it is the LunaRecycle Challenge is a $3 million, 2-track, 2-phase competition focused on the design and development of recycling solutions that can reduce solid waste and improve the sustainability of longer-term missions for NASA. Our phase 1 submissions are due March 31st, 2025. And again, for more information on rules and eligibility, please visit our website. All that information is captured there. There are 2 tracks in the LunaRecycle Challenge. Solvers may choose to participate in one or both tracks. In the prototype build track, solvers will ultimately develop a working prototype of a recycling solution. In the digital twin track, solvers will ultimately design a digital twin of a complete system for recycling one or more solid waste categories on the lunar surface and processing one or more end products. Last Monday, we did a webinar that was a deep dive into digital twins. And so that is currently posted on our LunaRecycle website. If you have an interest in reviewing that, please go there and you can access that. So again, I'm going to say this a million times. You can always find everything you need to know on our LunaRecycle website. So I'm going to now pass this off to Ray so we could get into the more interesting stuff. Thank you.
Okay, thank you, Chris. Can you hear me? Can you see me?
Yes, we can. Thank you, Ray.
Excellent. So as Chris has stated, I'm a waste management researcher at NASA Kennedy, but I have the unique opportunity today to talk to you guys from the space geology lens, to paint the picture as to where we expect the next crewed missions to land on the moon, and to help illuminate what implications may arise for any recycling solutions that you all come up with due to these environmental conditions. Next slide, please. So I'll give just a little bit of information as to why it may matter to you, and the reason is for the prototype track, you all have the option to choose one of 2 locations to implement your solution. Um, the first is outside directly onto the lunar surface itself, and the second is inside the pressurized habitat where the crew will reside. Now, each has their own pros and cons. Most notably, if you select to uh, utilize your solution on the lunar surface, you have much more space. You have the terrain itself to implement your solution. This also suggests that it'll be away from the crew, and so um, certain trash processing or recycling techniques may introduce additional crew hazards, which in turn would introduce increased mission risk. So if you are away from the crew, there's a potential for less risk overall for the mission. However, the caveat here is that you will also be indebted to the extreme ambient conditions of the lunar surface. And this is what we will focus on today as part of this presentation that I'm going to give you, is to explain what those environmental conditions are and how you can strategically align with them or within the pressurized habitat of the crewed habitat. And so to maybe give a couple moments on that, the advantages for implementing your solution into a pressurized habitat is that you are now in what we would call the shirt sleeve environment, meaning it is much more closer to Earth-like conditions where you have pressure, you have some oxygen and a nitrogen balanced gas atmosphere, and you also have temperature control. However, it does come with the caveats of being much closer to the crew. So any hazards or risks that you introduce with your solution are now right up close and personal with the crew. And you are also indebted to a restricted volume inside of the habitat that you need to make sure your solution can fit into. And so, again, there are pros and cons of each, and my goal for this presentation is to give you much more information as to what you would expect to experience on the lunar surface itself to help rationalize whether you want to use that as your implementation location or inside of the habitat. Next slide, please. Okay, Artemis 3 is the next crewed mission to the lunar surface, and there is a team of geologists here at NASA that are identifying which locations on the south pole of the moon are going to be the one that we expect to land at. And the latest news is that these 9 locations shown here on the left are the top candidates for this initial crewed mission back to the moon. These 9 locations have been down selected for a variety of reasons. 3 of them I've pointed out here, which are they're of high scientific interest, they have unique geologic characteristics, and they have the potential for volatiles, particularly water, so that we can extract and collect for either rocket propellant or to sustain ourselves there with life support system commodities, so water to drink, oxygen to breathe. And so you can see that each of these is kind of revolving around directly in the center of the South Pole. And so the poles particularly are suggested to have water in the permanently shadowed regions, which is of significant interest to NASA. Next slide, please. So what can we expect to experience on the lunar South Pole? The surface conditions are quite extreme, and so as I'm talking, there's this animation happening on the screen showing essentially the terrain that you get from the South Pole via the Lunar Reconnaissance Orbiter to give you, and I think ultimately visuals are paramount to understanding what it's going to look like, what it's going to feel like. And so as I talk, keep this in the back of your mind, and you'll see that the light in various regions of the South Pole is extremely dynamic. Some areas are permanently shadowed and never see sunlight. Others are almost always sunlit, and lots of the areas are kind of in between where they get sunlit for various portions of the lunar day and then go into shadowed regions for other portions of the day. So what does this mean? When you have uh, various shadowed times of your location, it will significantly affect the temperature that you would experience. And up in the from the Lunar Reconnaissance Orbiter and some analyses done by some researchers at UCLA, um, the temperature range is quite drastic, anywhere from 50 to 250 degrees Kelvin. Um, and you can see on the image on the top right, depending on which location is selected, you'll have different variations of hot and cold temperatures throughout the lunar day. But for all intents and purposes for this challenge, the consideration is that your solution should be able to accommodate the temperature range of 50 to 250 degrees Kelvin. Whether you're inside of the habitat or on the surface, you also have to deal with reduced gravity on the moon, gravity of roughly 1.6 meters per second squared. And then on the surface directly, the pressure is a near total vacuum. So this is in torr, which is 2 times 10 to the negative 12th torr, which is very, very high vacuum. So these are the conditions that you will particularly have to focus on to ensure that you can accommodate with your solution on the lunar surface. But there are also other factors like radiation from galactic cosmic rays or from the sun, or dust that needs to be mitigated and accounted for if you are to select the lunar surface as your implementation site. It should be noted that although radiation and dust are not necessarily required for the challenge as part of your design consideration, it is highly advantageous to come up with some um, preliminary strategies as how you will handle the dust problem, particularly if you choose the lunar surface. Next slide, please. And finally, again, for visualization as being paramount here, this visual will show the terrain mapping of the lunar South Pole. And so the colored regions show elevation, either gain or descent. So everything in blue is negative elevation into the craters. Everything in red and white are the high elevation, ranging from -8 to 8 kilometers. And so the South Pole is quite rugged. And to give maybe a little bit more context, the image on the right is Apollo 12 astronaut Alan Bean on EVA or on a spacewalk, and it should be noted that a lot of these Apollo missions were right around the equator, where it is much flatter than you would experience with all the craters on the South Pole, and so even with this quote unquote flat terrain, you can see how rugged it is even near the equator of the moon. So just additional context here, and all of these visuals are on NASA's website. So if you have interest and you're wanting to replay these, you can readily find them online and look at them, analyze them, and brainstorm how your unique lunar recycling solution may fit into the constraints of the lunar surface. So with this, I think that is my last slide. I'm very excited for this challenge. Best of luck. And I will hand it over now to Mike Ewert to talk a little bit more about the space waste story and what we have done internal to NASA thus far. Thank you.
Thank you, Ray. It's Mike Ewert at NASA's Johnson Space Center, and I'd like to go through a little more details on the waste materials that we're talking about, as well as some of NASA's current waste management activities. Next slide, please. So as you can imagine, NASA does a lot of research and development in different areas. The ones most applicable for this challenge, I would say, fall within our environmental control and life support systems area. And you can see 4 boxes there. In particular, within ECLS, we deal with waste in the life support category on the left. Of course, life support is about keeping the crew alive and healthy. And recycling can make this a more cost-effective and sustainable approach when we do things like recycle the wastewater. And then on the far right, we have a category we call logistics or logistics reduction. And these technologies are for that we're working on, try to reduce crew consumables, crew time, and also manage the waste. So anything we can do to recycle, reuse, or reduce helps save mass, volume, and crew time. Next slide, please. So as far as state of the art in space, the main thing we recycle is water right now. On the International Space Station, versus a little bit different environment in zero gravity, but which in some ways makes the water recycling more difficult. But on the International Space Station, we do recycle almost 100% of the water. And a fairly complicated diagram here showing the different air and water flows in the life support system. But just call your attention to the 4 dark blue arrows. Let's start with the one on the right side. In the air loop, where we have to take carbon dioxide out of the airstream to prevent it from building up, we reduce that carbon dioxide together with hydrogen in a process called Sabatier that can give us back some water. So that's first place we can recycle some water. Second one going to the left, but also in the air loop, is condensing the moisture out of the environment, what the crew breathes out. And then the other 2 are in the urine processing system. So we do take the urine and distill it to recover about 85% of the water from that process. And then we actually, in recent years, have an additional step called the brine process or assembly that recovers some more water out of what was left in the distillate from the urine processor. There are a couple of other smaller places where there's still some water, most notably in wet wipes and maybe moist towels or food, waste, a little bit of residual waste food has moisture in it that right now just go into the trash. Next slide, please. And we'll talk about those a little bit more in the research activities that we do have going on. But first, let me call your attention to what the waste stream is made of. Now, this is the solid waste stream. We just talked about water, but thinking about the solid waste stream. Starting on the right side, we can see the largest categories in the pie graph. Clothing, a pretty big one, so a lot of cloth. The food packaging, because we deliver food in individual packets for ease of preparation and storage. Those are the 2 biggest ones. Some other pretty large ones, towels and disposable wipes, and then a couple other minor categories. If we were to look at that in terms of the elemental breakdown, the majority is carbon, followed by nitrogen, oxygen, and other various waste elements. Next slide, please. To give you a little bit of visual idea of the waste that we're talking about, because these pictures are actually in microgravity on the space station. So get things floating around, we won't have that on the moon. But you can see that array of individual food packages on the left side. Their containers have a lot of plastic, but also some laminates with metal layers that help the food last longer. Bottom left, a maximum absorbency garment, we call it. Basically, when they have to go to the bathroom while they're in the spacesuit. Otherwise, if they're inside, they've got a not so regular, but a toilet to use that collects the human waste in most cases. Then washcloths, things like that. And on the right's a bunch of clothing packed up. And unfortunately, we don't have a laundry facility in space yet. So we just have to take enough clothing to last for the trip, and try to wear it for a couple of days to make best use of it, but eventually have to trash the used clothing. Next slide, please. Just real briefly, looking at this, you will find in the rules of the challenge, but these are the categories. We kind of simplified those waste streams to the most important, big ticket items in terms of what's going into the waste. Besides the ones I've already mentioned, like the plastics from food packaging, we also have foam that is used to protect things on launch. And then also, we think there will be some structural metal, not the main spacecraft structure, but maybe some of the secondary structure in the spacecraft or logistics module that won't be needed once it's landed on the moon. Or even unmanned landers on the moon, there may be an opportunity to recycle some of the aluminum, which is the main metal we use mostly in spacecraft. So you can find the details of what you're supposed to gear your waste processing systems toward in these tables in the rules. Next slide, please. Just a couple more pictures of the trash and how it's normally packaged into bags. They kind of squash it down into bags and make it as compact as possible. Go to the next slide, which leads into the first technology that I'm going to talk about that NASA is working on right now. We call it the Trash Compaction and Processing System. And so taking those bags, we can put it into basically a trash compactor, but it's also a heated trash compactor. So that helps reduce the volume, reduce the growth, any growth of biological activity, get rid of most of the smell, things like that. And very importantly, recover water from the trash, those wet wipes and a little bit of food that may be left. We actually have a contract to build this system with Sierra Space, and it's scheduled to fly on a test flight to the International Space Station around 2027. A couple of other manual trash compactors that we've experimented with as well that would just help reduce volume but not recover the water. Next slide, please. Next category of technologies that there's been a fair amount of work in, let's say, not full-scale systems. Some of them have been full-scale, I guess, but what we call lower technology readiness level are different ways to gasify solid waste. So we call it trash to gas. And this would help reduce the mass and volume of the waste products and potentially recover other resources that could be reused, such as water or oxygen. A couple that you'd find papers in open literature have to do with a project called Oscar, orbital syngas commodity augmentation reactor. And we're trying to build a full-scale ground system. We've done a microgravity test of a small-scale system on that process, which is basically an incineration process. Another one, there's a small business innovation research contract with a company called Cecilia Energy that is specifically looking at recovering hydrogen from plastics. Next slide, please. Several other trash to gas systems have been evaluated. You can see some references here. Incineration or gasification, plasma gasification, advanced organic waste gasifier system that Pioneer Astronautics worked on, microwave assisted pyrolysis, plasma pyrolysis, and torrefaction, which is a mild or lower temperature pyrolysis system. That one in particular focused on recovering water and dealing with some of the hazards of the human fecal waste. Next slide, please. Another technology that we are working on is the toilet itself. We call it the Universal Waste Management System. And there is a new unit that is undergoing testing on space station right now. It's also the toilet planned for the Orion human missions, like Artemis 2 coming up soon. Next slide, please. So that toilet, of course, is what's used to collect the urine and feces. And I already talked about, some of the ways we recycle the urine if we take it off separately. Then right now we do not recover anything from the feces, but we have, and basically we store it in metal canisters and dispose of it. So the far right picture on this slide shows a metal canister that basically collects all the poop, put a lid on it when it's full, and then it gets stored and disposed of on a resupply vehicle. It's sent away. But one thing we've done is build this alternate fecal canister that uses a soft side. And so you can see a flexible material there, so it folds up smaller, at least for launch. Of course, when it's full, it would still be the same size. But this might also provide the opportunity, with having the soft side canister, to put this into a processing technology, such as gasification, incineration, something like that. It still has a metal ring on the top, but someday we may be able to make it completely soft-sided so that it could be decomposed in another waste recycling process. Next slide, please. A couple of other technologies that could process the feces. Any of the ones that we talked about for trash to gas, incineration, steam reforming is the one I was trying to think of the word for earlier. Those could process feces as well as trash. And vacuum processing is another one we have tried in the past. Freeze drying, lyophilization, basically get the water out, make sure it doesn't smell anymore. And then same thing with torrefaction. There was some significant small business research work done by Advanced Fuels Research in recent years. So just to be aware that those things are out there. You can find more literature by searching public papers on those. And I think probably a little bit on these ones at the bottom as well. Supercritical water oxidation, waste oxidation, pyrolysis, and a company called Orbitech did a closed loop air drying system at one point. Next slide, please. And then real quickly, I'll mention, that clothing is something that gets discarded a lot. So we have thought about laundry. Basically, you have to make it pay off because you've got the water and the equipment and the power that are all needed to do the laundry. So we are working on that, trying to eventually come up with a laundry system that doesn't take very many resources. And so we've been working on that through some partnerships and things like that. Next slide, please. So to wrap it up on my part, recycling water is currently practiced on the International Space Station. On the moon, recycling will be even more important because it's even harder to get to. But there's additional opportunities for water recovery from the wet trash and feces, as well as a significant opportunity for recycling of more plastic, metal, and other materials. So that is what we hope you all will help us with. And with that, I'm going to turn it over to Romana Carey to talk a little bit more about how things are done on Earth currently.
Thank you, Mike. Good afternoon, everyone. I just want to talk a little bit about what we do here in Palm Beach County, Florida. Next slide, please. So the Solid Waste Authority is a dependent special district that was set up back in 1974. And we're an entity that's independent, actually, financially and legally. We don't get any funding from any other sources within Palm Beach County or outside. Next slide, please. So let me talk a little bit about the system we have here in Palm Beach County. We have 2 waste-to-energy facilities here, handling about 1.8 million tons of waste a year. We call them renewable energy facilities, or REFs. We also have a recycling facility, and we have a biosolids facility, and we have a landfill, which is the ultimate disposal location here after the waste is processed. And we also have 6 collection points, which we call transfer stations, because Palm Beach County is the biggest county in the state of Florida in terms of geographic area. And we also have 7 home chemical recycling centers where you can drop off like batteries and paint and home chemicals. And we also collect waste from unincorporated areas of the county. The county has 39 municipalities which do their own collection, but SWA is responsible for collection in the unincorporated areas. Next slide, please. So that is a map of Palm Beach County. As you can see, and it's fairly big, 2,200 square miles. Most of the population is along the coast there. So that shows the locations of the transfer stations and our main campus here on Jog Road in West Palm Beach. Next slide, please. So this is an important slide. Mike basically showed you exactly, how the waste composition looks like on your emissions, but this is Palm Beach County. Typically, on any given day, Palm Beach County, each person generates about 8.5 pounds of waste. And most of it is garbage, it's organic. And as you can see from this pie chart, we have a huge chunk of vegetation here, which is the 1.62 pounds per person per day. Because Palm Beach County, as I said, is large, and we get a lot of vegetation, yard trash, and also, especially after any storm event, we have significant amounts of vegetation that show up at our facilities, and also building debris. There's a lot of construction going on, and so construction demolition debris is also a big source there. And these are key categories here. And so we manage typically any given year close to 4 million pounds of waste. Next slide, please. So the waste to energy facilities are REPs. As you can see from the picture, we have 2 plants. The one to the left is the plant that's been operating since '89, 800,000 tons per day. And one to the right is our newest plant operating since 2015. That's 1 million tons a year. Next slide, please. So that's basically it. REF 1 uses RDF, or refuse derived fuel technology, and REF 2 uses mass burn. So there's combined capacity of 5,000 tons per day on our campus. And the power generation, combined is 163 megawatts out of these two facilities. And what we do is, we sell power to FP&L. And that's a big source of revenue for us. And we also recover metals pre and post combustion from both facilities. And there's also an advanced metals recovery. Once the waste is processed at these two waste energy plants, the ash is taken to the top of the landfill where we have metals recovery process there with magnets for ferrous and eddy current separators for non-ferrous metals. And we do pull out smaller fractions of both ferrous and non-ferrous metals from this operation. And whatever's left over is the bottom ash aggregate. And we also put that into use in construction to make concrete, which is basically for low strength applications, and also as an aggregate mix in asphalt for road construction. And what's remaining out of this process is a fraction of bottom ash and all the fly ash that's generated from the waste energy plants. And then we combine it and then we landfill that. Next slide, please. So this is our recycling facility. We call it Recovered Materials Processing Facility. As you can see from the picture, we have two different operations. Palm Beach County is what we call a dual stream operation. From a collection standpoint, we have two bins, a yellow bin that collects all the paper, fiber products, cardboard and everything, and the blue bin, which is also a curbside collectible, and that has glass, plastic, aluminum, and metal containers, food containers. And we handle them separately, we process them separately. Next slide, please. So the facility is about 138,000 square feet, and it's been in operation since 2009. And we process approximately 100,000 tons per year. And once we process and bale everything, we sell it to markets, and we keep all the sales proceeds. And we also have interlocal agreements with 39 municipalities in Palm Beach County. And since its inception, the program generated 20 million in funds. And we've shared more than 10 million with the municipalities. And as you can see from the slide there, Palm Beach County is ranked #1 in the state for recycling. So 2022, we're at 80%. And last year, we ended up at 84%. And so both of those numbers are #1. Next slide, please. So this is the biosolids processing facility. What we do is something along the lines of what you're thinking about, like reuse. We collect biosolids from 6 different partners, which is basically 95% of the biosolids generated in Palm Beach County. And the good thing about this facility is it uses methane that's generated from the landfill as a fuel source to dry the biosolids. And we sell this thing to fertilizer operations. Next slide, please. And the 6 partners that I mentioned, it's Palm Beach County Water Utilities, the East Coast Regional, and the South Central Regional, Boca Raton, Loxahatchee, and Seacoast Utilities. And this facility has been in operation since 2009. And any given day, we process about 600 wet tons. Synagro is the operator for this facility. And as you can see, roughly 190,000 tons is the throughput any given year. Next slide, please. This is our home chemical recycling center. As you can see from the slide here, people drop off their electronics, used motor oil, batteries, paint cans, and we make sure that this doesn't end up in the landfill, and we safely handle this thing, and we ship it off to locations where they can accept these hazardous chemicals. Next slide, please. So what are our keys to success here in Palm Beach County? The first thing I would say is a very good education program, and we also have public outreach initiatives, which is a key component. We are in different types of media, whether it's print or TV or social media, and we're there making sure there's a good message that goes around. And we also have year-round K-12 programs for school children. And they visit our facilities at least twice during their school years here in Palm Beach County. And we also have a program during summer called 4R, which is basically reduce, reuse, rethink, and recycle. And basically that brings some top middle school students, and we teach them about conservation and sustainability. And we do the same thing for teachers. We talk about new programs that they can incorporate into their curriculum and teach their students there within Palm Beach County. And consistent messaging is what we focus on throughout Palm Beach County, because we have 39 municipalities in Palm Beach County, and we don't want each municipality to do different things. So you have 39 different things going on. We definitely don't want that. So we have a consistent messaging, and we share the content with all the municipalities. So to make sure that, people do exactly the same thing within Palm Beach County, no matter where they live. And we also have a pretty good program to support construction, demolition, debris recycling. So last year alone, we recycled about 1.5 million tons of C&D debris within Palm Beach County. And the reason for us being number one in the state is because of this key component right here. C&D is a big aspect of recycling here in Palm Beach County. And also we do recycle vegetative waste. We send it to private operators outside, and they basically, they process it, mulch it, and some of that is land applied, and some of that is sold as mulch. And the key for us is waste reduction, right? So it's reduce, reuse, recycle. We basically, follow that theme there, and our goal is to minimize landfilling waste volumes. So very little goes to the landfill. So last year our diversion rate is close to 85%, meaning like just 15% of the waste generated in Palm Beach County ended up in our landfill, and most of that is ash, because that's the last resort. We process everything at the waste energy facilities, and then send the ash to the landfill. And we also maximize waste diversion. So by doing all of these things, we generate revenues, the key being power sales. We last year alone, we generated $50 million in power sales, and also close to $10 million in selling recycled materials. And there's also additional revenues that we're generating from ash metals recovery. These are the finer fractions, which are then taken to Europe, and they smelt it, and some of that is precious metals. So the value of those is like pretty high. And last couple of years, we have identified new sources of revenue by selling our renewable energy certificates and renewable thermal certificates. Basically, these are from power generation at the waste energy facilities, and also for reusing landfill gas. Basically sending it to the biosolids facility and using it as a fuel source for drying the biosolids. So it's not just one thing that we focus on. We focus on a lot of different things with the ultimate goal of maximizing landfill diversion and minimizing what ends up in the landfill, and also focusing on reduction of waste volumes, reusing, and basically rethinking the whole thing. Next slide, please. And that's all I have. If you have any questions, please feel free to reach out to me, and good luck with the challenge.
Hello, everyone. I just wanted to say thank you to Chris Frangione and our panelists today for their excellent and informative presentations. And for those of you who asked questions about eligibility or specific challenge rules and constraints, I would ask you to refer to the documents and links posted at the LunaRecycle website at https //lunarrecyclechallenge.ua.edu. And we'll also make sure that the website has a recording of this webinar as well, so this information will definitely not be lost. I'm going to open up the Q&A portion of this, which will take about 5 minutes to complete. And the first question, which I think Mike Ewart addressed some of this in his presentation, is what types of materials are we looking to recycle and what form would they be in?
Yeah, I think you've heard some examples of that. Pretty much a mixed waste stream. We would envision that astronauts could do some separation, but they couldn't spend a whole lot of time separating things.
Would we assume, like, if you had a towel that was worn out, it would be sent through a shredder before the team would get the material? What sort of form do you think it would be in?
It would be whole starting out, so any shredding operation would have to be part of your process.
Okay. Another question was how far into the ISRU process should the work continue? Meaning, do we take it from, a whole towel that's worn out to a fresh new towel? Do we incorporate some other materials into it? What do you think?
The rules addressed some of that. We were not intending it to necessarily go all the way back to original product, but getting it into a usable feedstock.
Okay. So this is for a lunar surface activity, and I know that we get to have inside and outside um, devices. So there's some questions in there about whether or not we'd have to accommodate the lunar environment, and if so, do you guys have any recommendations on where they could find information? Maybe we could post some extra resources. I know there's a few standards that NASA is using now that they might not be aware of.
Certainly, yeah, we can provide resources both for environmental expectations and things like express rack limitations and what that actually looks like. I know we put in some brief information on the rules document, but we could reference some of the standards that we use.
There was another question about washing clothing and what happens with all the soap material. Is there a process expected to remove all that?
I think it's fair to leave a wastewater stream. We have NASA has done some work, like I alluded to in the slides. We actually have a space agreement with Procter and Gamble looking at detergents that would be safe within our water processing system. So I wouldn't focus on the detergent or anything like that. But any other part of the system that is used to do something with the dirty clothing would need to be accounted for.
Okay. How about processing time? Is there a certain expectation for how long this process might take?
Is that following up on the clothing or the whole in
Clothing or the
general?
whole in general
General.
is the expectation of, a couple of days later you can get a 3D printed cup out of it, or instantaneous versus something that might take longer.
My perspective, if it's all automated and the crew doesn't have to be tending it, then it's okay to take a while. But if it's something that the crews need to be involved in, then you have to be a lot more conscious of the time allotment.
I'd also like to ask the panelists if they have any other final comments before we begin the wrap up.
I think I'll just add there were a lot of questions on what is in the trash, and I wanted to remind everyone there is a resource online that has all of the feedstocks listed and their material composition, and it also gives you the criteria on how you're graded for responding to the challenge. So there were questions about power in some of the chat. There was also a question on the crew time. So all of that actually gets compiled in your score based on innovation and actually answering the 365-day hypothetical mission scenario. So that's a wealth of resource. So please go check that out. It's available on the website. And of course, if you have any other questions, I think we can continue to take them. But I just wanted to chime in with that.
I guess one thing I would mention is thinking of the whole system and the implications on resource use. For example, as Romana talked about on Earth, do a lot of incineration or something like that. That process takes oxygen. So you have to think about that in a closed system. We don't have extra oxygen outside. So think about the entire system and what resources it needs in your solutions.
And maybe I'll add to this is that one question I saw in the chat that I haven't had a chance to answer, so maybe I'll answer it now, which was, you guys presented a lot of great technologies that you've already worked. Why not just use those? The intent is to kind of give you an idea as to what ideas we've come up with so far, and then allow you to say, hey, I think that this specific technique might be even better, and you might have a novel solution that we haven't even considered. So certainly the things that we have tried or investigated in the past are not all inclusive. So we're really curious as to the unique ideas that you guys come up with as compared to what we've done in the past.
And I wouldn't call them dead ends, things that we have tried. I think they're just, maybe not competitive enough with disposal options right now. So if you have an idea that's similar to something you've heard that we've tried, try to look at that literature and show how you could do even better. And then it might trade off.
Well, thank you all of our panelists. Elisa, if you don't mind pulling up the final slide, we'll start closing out. So we would love for you to get involved. And how do you get involved? First thing, visit our challenge website, LunaRecycle.challenge.ua.edu. Sign up for updates there. We'll let you know when we can begin to accept official registrations. There were a couple questions of where do I email my idea, or where do I tell you, how do I tell you or pitch to you? The only way to do it is through that official submission process, which again, we will be opening soon, and you can sign up to learn exactly when that will happen. Please review the challenge rules and guidelines. Those will really help you understand what we are looking for and how we are expecting things to come in. And then, of course, reach out to us with any questions about the challenge, eligibility, or technical requirements at LunaRecycle@ua.edu. That is the only email address where we can respond from. If a question comes in on LinkedIn to one of us or somewhere else, unfortunately, we cannot address it. So please make sure you are using that email address. And then we do have another webinar coming up in January. We don't have that scheduled yet, but we will post that on the LunaRecycle website. So keep going there for more information. Please share information about this with your friends and colleagues, and then stay connected with us on social media. That will really help you know what we have going on, and you'll be able to see what other activities we have going on. And our final request for you is when you log off, you should get a survey opened for you to ask how we can do better the next time. So that should pop up right at the end, or it will be emailed to you later. So thank you everybody for your time. Really appreciate you. We'd love to see all of these great ideas. As Mike and Ray said, we have some ideas, but there's a lot of really smart people out there in the world and in this group of people on this webinar. So please share your ideas with us, submit, participate, and hopefully you'll win some money and help us get to where we need to be to not have landfills on the moon. Thank you so much for your time, and this will officially end our webinar.